Okay, we have talked yesterday in class, or today in class, or in class, we did a kind of intro to exponential functions, which was super exciting, I'm sure you remember. So today we're going to actually get down to the nitty-gritty and actually look at some of these graphs. We're not going to do the entire take a closer look page. We're going to do like the front and like maybe one problem off the back. Okay, but I wanted to remind you of some key features. So if you could take a moment, get your notebook out. We're going to write some notes down real quick before we actually do the worksheet. All right, first of all, in an exponential function, the rate of change is multiplicative. So let me show you what that means, okay? So if I look at linear, my rate of change is additive, which means that I'm always adding to get to the next row. Now, obviously, when it looks more stable when I'm going up by 2, but my delta y over delta x is always, I can find it by adding. So my change in y is added. Okay. Now for quadratics, when my change in x is plus 1, which this one is, my second difference, oops, this should be 11, sorry about that. Okay. Okay. Anyway, so for this one, I have to go out 2 differences for it to be, for it to have the same additive increase. So my rate of change, I can't just look at the first difference, so I can't look at delta y. I have to look at delta y2, the second difference, to go out that far. So linear and quadratic, even still, I'm adding to get to the next row for those. But what makes exponential functions different is that I'm multiplying to get to the next row. So exponential, so far, of the functions we've seen, are the only ones that I multiply to get to the next value in my table instead of adding. Okay? So that's one of the things that makes them different, is that they have a multiplicative rate of change. One of the other things that I wanted to remind you of, and we kind of talked about this, we touched on this today in class, the start value and the growth rate must be greater than 0. Okay? Because if I start with nothing, I can't grow it or decay it. Like if I start with, like, let's say I'm talking about bacteria and I want to talk about the growth rate of bacteria. If I don't have any bacteria, they can't grow. If I'm talking about, like, you know, let's say we have trees that we're losing in the rainforest at a certain rate. If we're not losing, if we don't have any trees to start with, their rate can't decay. Okay? Likewise, I have to have a growth rate, because if I have, like, let's say I have, like, rabbits, and they're out in the meadow, and I'm like, boy, we got to talk about the growth rate with these rabbits. Well, what are they doing? Well, they're not growing. There's no growth rate. Well, then why are we having this conversation? I can't write an exponential function if I don't have a growth rate. So if there's no growth, I can't write a function. Likewise, let's say that, you know, I'm talking about, you know, deer population falling, or population in a small town of people falling. If the population in that town isn't actually, if the decay rate, the growth or decay rate is not changing, there's nothing to talk about. So if my start value is 0, then I can't grow anything. And if my growth rate is 0, there's no growing happening. So these have to be bigger than 0 in order for me to even be able to deal with this exponential function. Now the last thing, and we're going to talk about this very first on your worksheet, is that y values are going to approach 0, but they're never going to reach them. Okay, so they're going to get closer and closer and closer to 0, but they'll never reach 0. So we're going to talk about that. There's actually a term for what that means. So let's go ahead and real quick, let's go ahead and get out, take a closer look, which is the, whoa, that's not the right one, which is the worksheet that you picked up today. Take a closer look, and we're going to go through a couple of these examples. So first of all, I just told you that that the y values approach 0, but they never reach them. And remember, we talked about that today. We talked about how, like, if I have a paper, like if I'm, like, let's say I have a piece of paper and then I cut it in half. Well, I could cut, like, so then this piece is gone. I could cut this in half, and then this piece is gone. I could cut this in half. I still am going to keep having a small, now it may be a microscopic piece, but I'm always going to have a little piece left. And so because of it, I'm going to approach zero from a theoretical standpoint. I'm going to approach zero but never reach it. Now we know that from a practical perspective, there are things that, like money. The smallest thing we got is pennies. Okay, so we can't go any smaller than a penny in money because we just don't do that. So, there are practically, in the real world, obviously, there's going to be practical limitations to that. But theoretically, we would always be approaching zero, but we never actually get there. The line that we approach is called a horizontal asymptote. Asymptote. That is A-S-Y-M-P-T-O-T-E. Asymptote. So that's the line that it's approaching. And for most of our functions, it's going to be zero. But you can I believe I've seen one in the past where it was approaching 2 or something like that. So it's the line that your graph is getting slowly and slowly more close to, but you can tell it's never going to touch it. Usually, for our purposes, that line is y equals 0, but sometimes it's, I suppose it could be something else. But for our purposes, it's usually y equals 0. Okay, so that's what an asymptote is. So let's take a look at this first example. We're going to find some key features about this first example. Okay, so the number of people attending a carnival doubles each year. The table below represents the number of people attending annually. Okay, so how many people did we start with? Just by looking at this table, how many people were there before they started measuring this? What was at year 0? How many people were there? Okay, 30. We started with 30 people. So my initial value is 30. Okay, so that's my A. So remember, my parent function is A times B to the X, right? So if I were to write an equation, I'd say y equals 30. Now it says it doubles. So if it's doubling, what kind of function do I have, linear or exponential, or linear or nonlinear? If I'm doubling or tripling or halving every year, that means I'm multiplying by 2, right? Double means times 2. If I'm multiplying, that means I have nonlinear. Specifically, I have exponential. So what does that make my growth rate? Well, my growth rate when I double is 2. So my equation for this would be y equals 30 times 2 to the x. Okay, so let's kind of think about how we could build our table. Remember over here on our notes, we talked about how with exponential functions we build our table out by multiplying. So if the first year, if year 0 there were 30 people attending, it doubled. So how many do I have now? Well, I should have 60. If I double that, I should have 120. I want you to keep that table going and tell me how many people I will have after 4 years. At 4 years. Okay, so if I keep going, I have 240 here. And then at 4 years, whoopsie, I have 480 people. And then we already kind of wrote this. It's 30 times 2 to the x is my function. Okay, so what is my growth rate? 2. What is my x-intercept? Okay, when am I going to hit 0? Let's graph these points before we have that conversation. Okay, so I have a point at 0, 30. I have a point at 160, 2, 120, 3, 240, and then I ran out of points. Okay, what is my x-intercept? Do I have an x-intercept? Well, I don't have an x-intercept because remember, I see this happening here, but remember, this is continuing this way, and it's approaching 0. It's never going to reach 0, so I have no x-intercept with this function. So this function has no x-intercept, okay, because even though, like, this isn't part of my real-world situation, what's happening back here, I mean, I'm never going to go back here. But if I was just looking at this function, even still it has no x-intercept because it's moving closer and closer to 0 but never approaching. Okay? Is this data discrete or continuous? Well, where do I look to decide if something is discrete or continuous? Which variable, x or y? Well, I look at the x variable, so year. Now, this one is interesting because this data is actually discrete. And I'm wondering, some of you I think might have said, well, I think this data is continuous because we're talking about years. But this is where we have to actually think about this situation. Years are not always continuous data because think about this. The reason why is that carnivals are annual. So they don't happen all the time. They don't happen year-round. Most carnivals happen once a year, or they happen at a certain point. Well, since this carnival is annual, like the rodeo, for example, the rodeo is annual. So there's not rodeo happening year-round. It's only for that 1 3-week period. And so because of it, that 3-week period is the only time it happens. That makes it discrete data, which is why we're not going to connect up these points. Okay, so what is our domain? Do we have a limit to the numbers that we can pick? Well, there's a real world situation. So can I go back in time? Well, no. So I could look at 0 years, 1 year, 2 years, 3 years, 4 years, and so on. Okay, and that's what I see here in this table. Since it's discrete data, it's got to be a list. Okay, likewise, my range. In 0 years, I got 30 people attending, or 60, or 120, or 240, or 480, ... and so on. All right, so that's my domain. These are the key features, okay? I need to know that my y-intercept is my starting value. I need to know that this right here, so this is my start value. My y-intercept is where I start. This is how I change, how I grow or decay. Okay? And this is how many times I look at that. If it's 1 year, then I should be at 60 people attending. If at 3 years, I should be at 240 people attending. And this tells me how many years I'm going to look at. Okay? So let's look at the second example. Now for this one, do I have a situation that goes with it? I don't see one. So if I don't have a situation that goes with it, then I don't have any information. I don't have any information to limit this graph. Okay? So what we're going to do is we're going to use this function right here, and we're going to use it to fill in this table. So we're going to go to y. Well, no, we're going to go to y equals 200 times 0.75 to the x power. So remember, the exponent is up here. I saw a lot of people today writing it like this. That is not correct. This is not an exponential function, what you have written here, okay? Exponential functions have our unknown in the exponent position. I'm sorry, not squared. They have the x in the exponent position. Okay. Now, when I look at the table, I should see these values. So 0 is 200. The next thing they want me to fill in the table is 2, which is 112.5. Then they want 63.281, which is 4, and then they want to know what 9 is, which is 15.017. Okay? So now if I look at the graph of this data, when I look at the graph of this data, well, I don't know where the data is because it starts up at 200, so I'd have to adjust my window settings. But I can plot these points, okay? So if I plot, there's a point at 0, 200, right there. There's a point at 112, which is like right around there. There's a point at 463. There's a point at 915, which is like, again, I'm estimating. It's right about there. Okay? So since we're going down now, that means we have decay. First, I'm going to circle decay. And let's see if I just from looking at this equation, where do I see, where can I tell what the decay rate is? If I write a times b to the x right underneath this, a is my initial value, b is my growth rate or decay rate. I mean, it's basically the same thing. You can call it whichever one. Growth rate, you know, if it's growing down, it's decaying. Okay, so my growth rate is 0.75, or if you prefer fractions, 3/4. Okay, is this linear? Well, that is not a straight line. This is nonlinear. This is exponential. Okay, what was my initial amount? What did I start with? Well, I can see in the table the y-intercept is my initial amount. I can also see right here that A is my initial amount. Either way, I started with 200. Now, is this data discrete or continuous? Do I have anything to limit, to place limitations on this? I don't see a situation, which means any value that I put in is acceptable. That makes it continuous data, which means that I can connect these points. Okay? Now, which also means that they kind of go in every direction. Well, if they go in every direction, that means my domain is all real numbers. But is my range all real numbers? What did we talk about? Remember, we talked at the beginning about the asymptote, which is a y value that approaches but doesn't reach. Okay? What value in general am I usually approaching that I'm not going to reach? Usually I'm approaching the x-axis. That is usually my asymptote. So my asymptote is y equals 0. That means it's approaching that line, but it's never going to reach it. Well, since I'm above the y-axis, that means my y values have to be greater than 0. And they can't be equal to 0 because I'm never going to reach 0. Okay, it has to be greater than, but not equal to 0. So it has to be greater than. Okay? What I want you guys to do is right here, I want you to add range to this one. I want you to find the domain. I want you to tell me if it's linear. Well, I mean, what is it? It's exponential. I want you to tell me whether it's growing or decaying. I want the growth rate. Growth or decay rate. Okay. I want to know what it started at. I want the domain and range. Let's go. Well, I want to. Okay. Well, I think that's probably it. So that's what I want you to give me off of this graph. Okay. And then I want you to write down the word. I want you to write down Doug the dog. Is it Doug like that? Doug the dog. Okay. I want you to write down Doug the dog. All right. And I think you know what that means. And if you don't, well, I don't know what to say to you anymore. So go ahead and do all that, and I will see you on Monday. Have a good day. Have a good weekend.